Okay, so last video we talked about Kirchhoff's voltage law and the conservation of voltage for a closed loop. We also talked about resistor dividers, and today we're going to talk about Kirchhoff's current law, that is KCL, and that is the conservation of current. And what that says is if we look at a node here, that the summation of currents going into that node is equal to the summation of currents going out of that node. So what's going in is equal to what's going out. So we can start to look at this problem here, and we know from last video that electrical current will flow from the positive side of the battery to the negative through every path possible. So we know that the current will go down this path, and it will also go down this path. So that really allows us to say that we have I1, which goes from the battery to this node. We have I2, which goes through the first resistor, and then we have I3, which would go through the second resistor. So we can write our equation like this and say I1 is equal to I2 plus I3. Well, we know that I2 is going to be this voltage over R1, and I3 is going to be this voltage over R2. So we can say that I1 is equal to V over R1 plus V over R2. We can simplify that one step and say that we are equal to this. And if we take V divided by I1 and put this on the other side, we'll have V over I1 is equal to 1 over R1 plus 1 over R2. We know from one of the earlier videos that for resistors in parallel, that this would be the equation for the total resistance, RT. Now we can put I1 on the other side and have V equals I1 times RT. And we notice the familiarity with Ohm's law, where V equals IR, except now we have these subscripts I1 and T. So KCL is really the conservation of currents, so what's going into a node is what's coming out of a node. We can look at probably the most basic example you can find of KCL, where we have this circuit here, and we want to find all currents and the voltage point VA, which is this node right here. So once again, our current goes from positive to negative side of the battery. So we know that the current will be going this way, it will come down, and then it will come down here. So we can label the currents as this. If you label the currents incorrectly, the math will actually correct itself. So we can start setting up some equations. We can say I1 is equal to I2 plus I3. And now we can also implement KVL. So we can have two loops here. This first loop, and then this second loop. So call that 1, and this is 2. And for reference, we will put our ground here. So we know that we have current going through the resistor, we will have a voltage drop over it. So we can label the resistors like this, and I put this vertical on here as if you're looking at the resistor sideways. You can surely have it going horizontal if that works for you. So we can start with the first loop. So start in this bottom left corner. And we know that we will be going up some voltage V, and then we will be minus I1 times R1 minus I2 times R2, and that will be equal to 0. So we start here, and we just follow this loop back down to 0. We can look at the second equation, where once again, we can start at this node, and we can go up. Now notice here, the polarity that we put the current going through is negative, or opposite, so we can really put a negative sign to that. And we can think of that as, well, if we have start here and we go up to this point, we have minus to plus, so we have the positive. Kind of apply the same thing to here. We have minus to plus, so that will be a positive. So we will have I2 times R2. But then when we come back down, we're going positive and negative, so we put minus I3 R3 equals 0. So we now have 3 equations and 3 real unknowns if we know what V and all the resistors are. So the first one we can look at is the second one. We can say I2 equals I3 times R3 over R2. So that will be our first equation that we use substitution on. Then we can plug that in here to say I1 equals I3 R3 over R2 plus I3. Or we can bring this one down and say I1 equals I3 R3 over R2 plus 1. So now we know what I1 and I2 are in terms of I3, which allows us to plug both of these into equation number 1 that we have here. So we can say V minus I3 R3 over R2 plus 1 times R1 minus I3 R3 over R2 times R2 equals 0, where I1 is equal to this, and I2 we know is equal to this. So we can simplify that a little bit more and say V minus I3 R3 over R2 plus 1 times R1 minus or plus R3, because our minus sign we factored out, equals 0. What this allows us to say is that I3 is equal to V over R3 over R2 plus 1 times R1 plus R3. So now what we can do is we know what I3 actually is now because we know what V is, we know our voltage, and we should know all the resistors. Those should be given in a problem like this. So we can find out what I3 is. Based off of that, we can find out what I2 is, and we can also find out what I1 is. Now we can look at this first loop again, and we can actually look at this first equation, and we can rewrite that as V minus I1 times R1 minus VA equals 0, because this voltage to ground is just VA. So we can say that VA equals V minus I1 R1, which equals V minus I3 R3 R2 plus 1 times R1. And we know that this equals V minus V over R3 over R2 plus 1 times R1 plus R3. And then we have R3 over R2 plus 1 times R1. So this is what VA is equal to. So that's how we apply KVL, KCL to do some basic circuit analysis. So we know what our nodes are, we're able able to estimate what our current direction should be, and then we write out the equations, make the substitutions, and we can find out our answer for everything. So now we know what I1 would be, what I2 and I3 would be. We also know what VA is based off of the input voltage that we're given, and then all the values of each resistor. So next time, we can look at a circuit like this, where we will have one voltage source over here and the other over here. Again, we want to find I1, I2, and I3. And notice that we have current going from here and wants to get to the negative side of the battery. So we can say this current goes this way, this current will go down to come back. And then we can say, because we have another battery here that's positive to negative, that current would want to go this way. So now our loops would be this one, and then this one. We'll also look at what happens if we label our currents incorrectly and how the math will correct itself. So I think that's good for today.